we're going to be looking at some chemistry calculations, in particular atom economy, yield and titration calculations. So if you're in my class, you will hopefully have attempted these questions before, but if not, you can see the questions, pause and have a go as we go through. So question 1, we have a student investigating a reaction between copper carbonate and dilute sulfuric acid, and we can see the equipment set up there. And we're asked to complete the state symbol. So copper carbonate is a CuCO3, and we can see that is solid. And then we've got water, which would be liquid. Now, big exam tip here, they were very particular about this last year. State symbols must be lowercase. So you might get away with an S, either upper or lowercase by itself, but with the L's and G's, they will be looking to see that you are using lowercase letters. So why did the balance reading decrease? That is because we had a gas being lost from the flask. Okay. We're then asked to work out the percentage atom economy of copper sulfate from copper carbonate, and we're given the formula, which is really helpful, and we're given all the relative formula masses. So it's just a matter of plugging those numbers in. So relative formula mass of copper sulfate, because that's the desired product, divided by the reactants. So we get 159.5 divided by 123.5 plus 98, and we times that by 100, and that gives us 72.01%. Give one reason why it's important for the percentage atom economy reaction to be as high as possible. So they'll give you marks for multiple reasons. Anything from it's important for sustainable development, because we want to minimise waste, for economic reasons, so making it cost effective, and also waste products could be pollutants, greenhouse gases, all of those sensible answers. Next question, this is also a level 1 question, and by level 1 I mean you'll find this on foundation papers only typically. You will recognise if you look at the higher foundation papers from the same year that there is a lot of overlap, they just may be phrased slightly differently. So you might get a multiple choice in the foundation paper, but if you're doing the higher paper, this might not be a multiple choice question. So, ethanoic acid is a weak acid. Draw a ring round the correct answer to complete each sentence. So, when dissolved in water, an acid forms a solution containing hydrogen ions. Hydroxides would be alkali, okay? Ethanoic acid is a weak acid because it is only partially ionised, okay? So here we are looking at a titration. We've got an experiment set up. We've got some sodium hydroxide solution in that piece of equipment called A, and we've got a conical flask at the bottom containing our vinegar and our phenolphthalein. So draw a ring round the name of the piece of apparatus, which is A, that is a burette. Okay. You then ask, what type of substance is the phenolphthalein? And you're told it's been used so we can see the endpoint. That is an indicator. So how would you know that the endpoint of titration has been reached? Well, you'd see a colour change. Now, in the foundation paper, they'll give you credit just saying for colour change. In the high paper, they'd expect you to say it goes from clear, colourless to pink. Okay, you tend to want to put down what the before colour was and what the after colour is. So we have some results from the titration calculations. They've done a rough titration, that's your kind of quick first draft to kind of get approximately where you need to start slowing down. And then they've had 3 subsequent results. And those results are concordant with each other, they're within 0.1 of each other, so we can use all of them. There is no anomalies here, which is rare for a mean calculation. But as we said, this is the foundation paper question, so maybe they're being a bit nice. So calculate the mean value, so you're going to add up those 3 numbers, divide by 3, and you get 20.4. We're then asked to calculate the mass of ethanoic acid in 1 litre of vinegar. So we've got to think, how many times does 25 centimetre cubed fit into 1 litre, or 100 centimetre cubed? So 1000 divided by 25 equals 40. So that we then go, okay, 1.25 times 40, that gives us 50 grams. So we are now moved on to a level 2 question, and this could appear in both the higher and the foundation paper. So we're given a lot of information in this question, and we're shown 2 methods for obtaining zinc sulfate. And we're also, like in the early question, given the equation for percentage atom economy, and we're given some data. So they ask us to give our answer to 3 significant figures, the percentage of atom economy for making zinc sulfate with method 1. So we're not looking at method 2 here. So we're going to plug those numbers into the equation and we get an answer of 89.94. Now this question is worth 3 marks. I would only get 2 marks if I left my answer like that. Can you see what I've done wrong? They've asked us to give our answers to 3 significant figures. So I need to get full marks, say 89.9. We're then told that method 1 gives a high percentage atom economy for making zinc sulfate than method 2. Give a reason why it's important to use a reaction with a high atom economy. So anything along the lines that it's more sustainable or there's going to be less waste. We then are told that the student uses 50 centimetre cubed of zinc sulfate solution with a concentration of 80 grams per decimetre cube. What mass of zinc sulfate is dissolved in 50 centimetre cube of this solution? So you can approach this in different ways, knowing that decimetre cubed is a litre, and then work out ratios, or you can use your triangle. And then we know that mass equals concentration times volume. The mass then equals 80, which is our concentration, times 50 divided by 1000. Whenever we are doing these calculations in chemistry, we need to make sure that our volumes are in decimetre cubed. And we get a mass of 4 grams. So we're now moving on to level 3 questions here. These are only found on the higher paper. So we are given some details about aspirin and we're given a method for making the mixture there and we're given the equation. And they ask us to calculate the maximum mass of aspirin that could be made from 2 grams of salicylic acid. And we're told the relative formula mass of salicylic acid and aspirin there. So we can look at the ratios in the equation and see that all these things have got a 1:1 ratio. So that tells us if we had 1 mole of salicylic acid and everything went perfect, we would make 1 mole of aspirin. So how many moles of salicylic acid do we have? Well, we can use our triangles again and use our mole equations, and we've got mole equals mass divided by mR. So mole equals 2 divided by 138, and that gives us 0.0145 moles of salicylic acid. And as we said already, moles of the acid equals moles of aspirin, so we know our moles of aspirin. So we can now work out the mass because we know the moles and we know the mR, and that gives us a value of 2.61 grams. The exam board will accept a range between 2.5 to 2.7, and that's largely due to a rounding error, so there is some tolerance there. We then have our next question where the student only made 1.1 grams of aspirin from the 2 grams of salicylic acid. Calculate the percentage yield of aspirin for this experiment. So the student got 1.1. We know from our last question that it should be 2.61, so we times it by 100 and that gives us 42.15%. So percentage yield is basically what you got divided by what you should have got times by 100. We're then asked one possible reason why this method does not give the maximum amount of aspirin. There could be errors in weighing. Some of the aspirin might be lost. You're going to think of stuff being stuck to side containers and so forth. Not all the reactant may have converted, so it might not have been a complete reaction. The reaction is reversible, so we may be getting other products, chemicals being produced. Any sensible suggestion there? So our next question, again, level 3 higher paper only, and we are asked first to describe a titration. So if you want to pause and read through that, you can do, but I'm just going to focus on the calculations today. So we're told the acid in 25 centimetre cube of champagne reacted completely with 13.5 centimetre cube of sodium hydroxide of a concentration of 0.1 moles per cubic decimeter. Calculate the concentration of acid in the champagne, and we're assuming that 1 mole of sodium hydroxide reacts completely with 1 mole of acid. So that tells us if we know the moles of sodium hydroxide, that's going to be the same as number of the moles of acid. And we know that concentration equals moles divided by volume. Like I said earlier, the mole triangles which I put on the side are not credit worthy in the exam. You need to write out the equation you are using to get the credit. Now it's all very helpful. I find it helpful to draw the triangles out when I do a question, but I know I have to write out it in concentration equals to get the mark from the examiner. So moles of sodium hydroxide equals concentration times volume. So that's going to be 0.1 times 13.5 divided by 1000, and convert to decimeters again, and that gives me a value of 0.00135. So the concentration of acid is going to be 0.00135, because moles of sodium hydroxide equals moles of acid, divided by 25 divided by 1000 equals 0.054 moles per decimeter cubed. So you're then asked, is the analysis by titration enough to decide whether the champagne is safe to drink? They just want a sensible answer. You don't know, not enough evidence or words to that effect. Any sensible answer saying, well, the acid levels might be safe, but there might be other issues. You might want to talk about bacteria. We don't know if there's anything grown in there. There's a lot of flexibility with this. Right, we have a beautiful graph here showing the endpoint of this reaction, and we're told phenolphthalein is an indicator used in this titration, and it changes colour between pH 8.2 and pH 10. Methyl orange is another indicator. It changes colour between pH 3.2 and 4.4. Suggests why methyl orange is not a suitable indicator for this titration. So anything along the lines of, or first mark is for, methyl orange would have changed colour well before the endpoint. There's also a weak acid present, so methyl orange is much better to be used with a strong acid weak base titration. So question 6, again level 3, higher level question, and we are talking about airbags and the reaction which produces nitrogen gas during an accident. So the mixture contained sodium azide, which decomposes on heating to form sodium and nitrogen. A typical airbag contains 130 grams of sodium azide. Calculate the mass of nitrogen that would be produced when 130 grams of sodium azide decomposes. And we're given some data there that you could pull off a periodic table. So I'm looking at this equation, and I can see we've got a ratio of 2 to 2 to 3. So that if I had 2 moles of sodium azide, I would produce 3 moles of nitrogen, and that's going to be useful later on. So I need to work out how many moles I have of sodium azide first. So that's going to be mass divided by MR, so 130 divided by 65, that equals 2. So that fits really nicely into our ratios, so that I had 2 moles of sodium azide, I'd have 3 moles of nitrogen. So I've got 3 moles of nitrogen. So the mass is going to be moles times MR, so that's going to be 3 times 28, and that gives us 84 grams. So 1 gram of nitrogen has a volume of 0.86 litres at room temperature and pressure. What would the volume of nitrogen be produced from our 130 grams of sodium azide? So we're using our answer to the previous question, but actually they've given you a number to work with if you didn't manage that, and I think actually everyone would be able to have a go at this question, higher and foundation students. So we have 84 grams of nitrogen, so we're just going to do 84 times 0.86, and that equals 72.24 litres.